Hello, my name is Riley Van Dong. I'm a research assistant for Professor Nazar at Brock University, and today I'm going to present the N-lane bridge performance antipattern analysis using system-level execution tracing. Multi-threading is a very useful technique in programming. It takes full advantage of multi-core systems and allows for multiple tasks to be completed at once and increases the throughput of the application. However, if it is used incorrectly, it can actually add latency to the application. And to make matters even worse, the cause of this latency can be very difficult to determine. This is due to the many possibilities for the latency, such as lock contention, resource pool limitations, or CPU preemption. Additionally, non-determinism means that it is not trivial to follow the execution of a multi-threaded program. As a bit of background knowledge, I'm going to be talking about two distinct concepts researchers have created to describe problems in applications. The first is bad smells. A bad smell can be defined as a surface indication of a deeper problem within the system. Bad smells are often called code smells, and this is because they are closely related to static analysis. The bad smell must be directly identifiable in source code. Some common examples include duplicate code and feature envy, where one class too often makes use of another's features. And previously, we worked on detecting runtime smells using execution tracing. Some examples of these smells we detected were CPU hog and priority inversion. And if you'd like to check that out, you can look at the link there. The other concept that researchers have come up with is antipatterns. An antipattern is a common problem bundled with detection methods and common solutions, and is used to better describe issues in a piece of software because the detection methods and solutions come with the actual problem. An antipattern analysis is performed during the testing phase of an application before the delivery of the application. Unlike bad smells, it does not need to be linked to a specific location in source code. An example of an antipattern is the one-lane bridge, which is a performance antipattern. This is a place where only one or a few threads can execute. The one-lane bridge antipattern describes the bottleneck issue in an application. It is similar to a real-world one-lane bridge, where only one car can pass at a time. It also shows how to detect the bottleneck and how to fix it. However, the concept has some challenges in existing research. First, it only considers bottlenecks in passive resources, not active resources. What I mean by an active resource is a resource which performs a physical action in the real world, like a CPU. A passive resource exists only virtually, for example, a lock or mutex. The second challenge is that existing research uses imprecise metrics. For example, the overall CPU usage is used to denote an application's CPU access. However, this only takes into account the best case scenario. If there are other applications running at the same time, or the CPU is undergoing CPU throttling, this metric is incorrect. In order to address these challenges so that we can use the one-lane bridge antipattern to diagnose multi-threading issues, we first introduce the N-lane bridge, a new category of one-lane bridge. This new category extends the one-lane bridge from passive resources to active resources. It also defines a method to distinguish an N-lane bridge in the target application from issues due to an external application. Second, we introduce a detection method using system-level execution tracing that will be performed during the testing phase. It allows us to gather more precise metrics and also eliminates the need for the manual instrumentation of source code with trace points. So what exactly is an N-lane bridge antipattern? An N-lane bridge antipattern is a performance bottleneck caused by the target application's use of an active resource. But an active resource can also be congested due to external activity. So, cases where the bottleneck is due to an external application's use of the active resource are not considered n-lane bridge antipatterns. Some probable causes of the n-lane bridge include an incorrect configuration of the software, or the implementation of the software didn't account for the system that it would be running on. And why exactly do we focus on system-level tracing? It has three benefits. First, concurrency is difficult to predict, and static analysis would have to rely on abstraction. Dynamic analysis eliminates the false alarms that would result because of this. Second, system-level tracing provides the wide visibility of executing threads, processes, and resources needed to accurately analyze multi-threaded applications. Techniques like application-level tracing or profiling would not provide the same wide scope of visibility. Finally, the trace points are predefined for system-level tracing. For example, the Linux kernel has trace points predefined, so no extra effort or domain knowledge is needed in this case. The flowchart on the left shows our detection strategy for traditional one-lane bridge as well as n-lane bridge antipatterns. I'll go over this method in more detail, but basically there are 6 different steps and 3 different possible outcomes, being an n-lane bridge antipattern detected, a one-lane bridge antipattern detected, or no problem detected in the application. The application I will be demonstrating our method on is a personal banking application called InDebitO. It can be downloaded at this page. The application includes functionality to add incomes and expenses, but we will just be testing the login functionality. Because the one-lane bridge is a scalability problem, we need to do a number of traces and each increase the number of users. So we'll increase the number of users until either the response time has increased 10 times its original number, or the application no longer supports adding more users. And when we collect the traces, we'll need to enable the following trace points. All syscalls, especially the interrupt syscalls because we'll need them later, the request delimiters, sched switch, and sched wakeup. I'll be using Apache JMeter to send the requests. We'll start with just one concurrent request, and then each time we'll add 5 more. And each request logs into the same account using the following credentials. As you can see, the first run with just one request took 289 units of time. I think it's milliseconds. At 21 concurrent requests, the response time is over 2,890, the average response time, so it's time to stop collecting traces. The next step is called metric extraction. We need the response times of the requests, as well as the critical blocking times for the threads handling the requests. In order to find these blocking times, we compute the critical path, as can be seen on the picture along the bottom. We want to find the response time metrics first, because these will tell us which traces we need to find the blocking time metrics from. And luckily, Apache JMeter records the response times in its logs, so I've copied those over to this document here. The next step in the process is called the response time analysis. We record response times because, as the graph on the left demonstrates, both categories of one-lane bridge cause increasing response time latency as more users stress the system. What the formula on this slide is saying is that if we come to a point where every time we add more users, the response time of the system increases significantly. Then we continue with our analysis. And comparison of response times is done using a two-tailed t-test. I've written a script to perform the t-test for us. It will be available in my GitHub page that is linked at the end of the video. It takes data in this format. Let's try it out. So, the response times start increasing at the second trace, so when there are 6 concurrent requests. So in the last step, we established that a one-lane bridge antipattern exists in the system. Now we want to find which resource that one-lane bridge is connected to. What the formulas on this slide are saying is that whichever resource added the most increase in latency over the sequence of traces is connected to the one-lane bridge. And importantly, we want to discover whether this resource is an active resource or a passive resource. Here I have the blocking time metrics extracted. I use this crit path data script, but it takes a long time, so I just skipped over it. I've written a script to compare the blocking times, and once again that will be available in the GitHub. And it takes data in this format, which came from the other script. So let's run the script. And the CPU is the guilty resource. Because the CPU is an active resource, the active resource congestion analysis will be our final step. Basically, we want to discover if the target application has an n-lane bridge or if the congestion in the CPU is due to external applications. We will do this by looking at the CPU usage. If the in-debit-o application holds the CPUs for over 50% of the request duration, we can say that there is an n-lane bridge. For this analysis, I looked at the last trace that we recorded, and then I used the CPU congestion analysis script on it, which will look at which processes were using the CPU during the request times. And I got these results. So external processes use the CPU for a total amount of this time, and the target application used the CPU for a total amount of this time. And this means that the target application used the CPU for 86% of the request times, meaning that there is an n-lane bridge. Now, because the offending resource was not a passive resource, we don't actually have to do the call stack analysis. But if it were, we'd look at the trace point address given, and we'd subtract from that the base address, and that would give us the ELF symbol table entry. Now, if we got 4040, we'd know that the offending address would be named lock in the source code. Using our method, we were able to discover that there is an n-lane bridge in the login process for in-debit-o. When only a few users try to log in at the same time, there is a lot of latency. Therefore, it would be a good idea for the developers to try and implement a less CPU-intensive method for logging in. And that's the end of the demonstration. We have written a paper on this subject and have submitted it to the ICPC 2022 conference. In the future, we would like to improve our work by changing the metric extraction algorithm to form and examine the critical paths in batch jobs instead of individually, in order to reduce the amount of time it takes for this step. We would like to add to this method by detecting more performance antipatterns, such as the traffic jam and the ramp, which are very similar to the one-lane bridge. And that's the end of the presentation. If you have any questions, please feel free to email me, or you can check out my GitHub repository. Thanks for listening.